So in several samples that we took, you should notice some of the following. So in each case, the population mean was 25 in all three cases. So mu was equal to 25. Okay, so if we go back to the very first sample, that was, again, this was when I had typed up the notes here, but again, this is our population mean. So this is mu sub x is 25. And then we took a sample of 10 and got a mean for that sample here. That was our value of x bar. We also displayed here because it was just that single sample that we did. Okay, so again, this is just based on that one sample that we did. Okay. In the next one here, again, we started with the same uniform distribution where the mean of that distribution, so mu, was 25. Again, we took a sample of size 10, so this is little n. We took one sample of size 10, and in this case we got an x bar value of 28.3245. And then in the third trial that's in the textbook, here again we started with the same population uniform distribution over 0 to 50, so the mean of that distribution, so mu, is 25. Again, we took a sample size of 10, so little n is 10. And we took one of those samples, and we got an x bar of 31.7097. All right, so in all three cases, we started with a population where mu was 25. So mu, or again, if we subscript with the random variable notation, mu sub x. In the first sample, the sample mean was 22.9438 minutes. So here the value of the sample mean, and our symbol for that is x bar, is an underestimate for the population mean mu. Okay. Underestimate because mu is actually 25, but if we were to use x bar as an estimate, we'd think that the population mean was somewhere near 22.9, so a little bit smaller than what it actually is, so an underestimate. In the second sample, the sample mean was 28.3245. Okay, so here the value of the sample mean x bar is an overestimate of the population mean mu. Because again, x bar is trying to give us a good estimate of what the true value of mu is, which in this case with the simulation we actually know what it is. Mu was 25. So in this case 28.3245 is bigger than 25, so we have an overestimate. And finally, in the third sample, the sample mean was 31.7097 minutes. So here the value of x bar, again, is another overestimate of the population mean mu. So this last bullet here is important. Okay, so random samples are different from each other. Okay, as we just randomly go and talk to people and take measurements, you know, the 10 people I talk to are going to be different than the 10 people you talk to. So again, as long as we're using random sampling techniques, you know, we've got good sampling techniques in there, but still our random samples are going to be different from each other, which means that they're going to tend to give us different values for the statistics that we compute from those data sets. So like here we can see each time we push the button, we got a different value of x bar, even though every time we sampled from the population with a mean of 25. Okay, so this is known as sampling error, which I've never liked this word because error sounds like you made a mistake, and you didn't. Okay, this is just the natural tendency for samples to be different from each other and to be different from the population from which they are taken. So in the case above, we've got each one of our sample means they were different from each other, and all three of these were also different from the mean they were trying to estimate, which was 25. Okay, we never actually got a sample mean that was exactly right on the mark of 25 that we had for our population. Okay, and that's not because I was a bad button pusher or you were a bad button pusher. Okay, it's just because the samples are random. So the sampling error is the natural tendency for samples to be different from each other and to be different from the population from which they are taken.